Welcome. We are studying our fifth chapter, multiple integrals. Today we shall study fourth module, change of variables in double integral. In the earlier module we have studied Green's theorem. In this module we shall apply Green's theorem. We start this module by recalling Green's theorem. Let C be a piecewise smooth Jordan curve and R denote the region bounded by C along with the trace of C. Let capital A be an open set in R2 containing the region R and capital A from A to R2 be continuously differentiable. If M and N are the components of F, then line integral over C m dx plus n dy equals double integral over R del n del x minus del m del y dx dy. Now, Green's theorem establishes a relationship between the line integral around a simple closed piecewise smooth curve C and the double integral over the plane region D bounded by C. This result will be used in this module. Let us recall some results we studied in single variable calculus. Let f from I to R, g from j to R, where j contains the range of the function f. Also let h equal to g compose f. From chain rule, we know that if both g are differentiable, then h also. Moreover, for every possible x, h dash x equals g dash f x, f dash x. Now, if there exists a function p such that p equal to g dash, then using the above we can write h dash x equal to p of f x f dash x. Since p is g dash, this means integral over px dx equal to gx plus c can be restated as integral p f x f dash x dx equal to g of f x plus c, where c denotes arbitrary constant of indefinite integral. Writing df for f dash x dx, combining the above two, we can write integral px dx equal to integral pf df. Loosely, we can say that in the above we substituted x for f or f for x. We can also derive similar results for definite integrals. We mention the result here. Let f from I to R, g from j to R, where I and j are open intervals satisfying fi subset of j. We further assume that f is continuously differentiable on I and g is continuous over j. Then for all a and x in I, integral from a to x g f b f dash v dv equals integral f a to f x g u du. We can alternatively write as a to x g f df equal to integral f a to f x g u du. Clearly, we are discussing method of substitution for integrals. With this method, we transformed comparatively complicated integrals into reasonably easier ones. In case of evaluating double integrals, such formula is also available. Our intuition says this would be rather more complicated as we have to consider change in two variables. Let us consider a double integral over S f x y dx dy, where S is a bounded region in R2. Suppose we prefer a simpler integrand capital F u v. So, we have to undergo substitutions like x equal to x u v, y equal to y u v. Now, these substitutions will transform the region S to another, say T. If these two equations of substitution can be solved for u and v in terms of x and y, we can write u equal to u x y and v equal to v x y. In such cases, we assume that the maps x and y between the regions S and T are bijective and hence invertible. Unless otherwise stated, we shall consider only this type of maps in the remaining part of this module. First, we shall mention the formula and later go through a proof. We assume that x, y, u, v are continuous and possesses continuous partial derivatives at least up to the second order. The required formula is double integral over S fxy dx dy equals double integral over T f x uv y uv modulus of del xy del uv du dv, where almost everywhere on the set T the Jacobian determinant del xy del uv is non-zero. That is, del xy del uv equal to determinant del x del u, del x del v, del y del u, del y del v is non-zero everywhere on T except for a set of measures 0. First, we shall prove the result for a constant scalar field f such that fxy is identically 1 for every xy in S, where S is a bounded rectangular region. Result: let S denote a bounded rectangle in xy plane. We consider two invertible functions uv from S to R2 given by u equal to uxy, v equal to vxy, whose inverses are given by x equal to xuv, y equal to yuv. Let these maps transform a region S into another T. We further assume that first, x and y have continuous second order partial derivatives. Secondly, the Jacobian determinant del xy del uv is never 0 on the set T. Then, double integral over x dx dy equal to double integral over T modulus of Jacobian del xy del uv du dv. We give a proof. First, we assume that the Jacobian is positive. Given del x del u, del x del v, del y del u, del y del v are continuous. As polynomials are continuous and composition of continuous functions are also continuous, it follows that the Jacobian is also continuous. Moreover, as the Jacobian del xy del uv is never 0 on T and continuous, it follows that it is positive everywhere on T. Next, let M and N be two continuously differentiable scalar fields on S. Clearly, del S is a piecewise smooth curve because it is the join of 4 line segments. Then by Green's theorem we have line integral over delta S m dx plus n dy equal to double integral over S del n del x minus del m del y dx dy. In order to apply the above result, we employ scalar fields M and N satisfying del n del x minus del m del y equal to 1 everywhere on S. Thus, we can evaluate a double integral by a line integral. The reason is that we know line integral is as good as an integral of one variable. Moreover, we can use method of substitution over a single variable integral. Let for every xy in S, mxy is 0 and nxy is x. Then by Green's theorem, putting these values of m and n, we find integral over S 1 minus 0 dx dy, that is integral over S dx dy equals with line integral over delta S x dy. On the other hand, we can express the Jacobian del xy del uv as del del u x del y del v minus del del v x del y del u. Consequently, double integral over T modulus of the Jacobian delta xy del uv du dv equals to integral over T del xy del uv du dv because it is positive everywhere. So, this equals to line integral over delta T x del y del v du plus x del y del u dv by using Green's theorem. So, in order to prove the theorem, it remains to prove that line integral over del S x dy equal to line integral over del T x del y del v du plus x del y del u dv. Here we assume that del T is a piecewise smooth Jordan curve and can be expressed by del T equal to gamma from AB to R2, where gamma equal to gamma 1 gamma 2 and gamma A equal to gamma B. Now, we consider a continuously differentiable transformation f from T to S, which carries T onto S and del T onto delta S, satisfying the above condition. That is the positiveness of the Jacobian determinant. By this transformation, gamma equal to gamma 1 gamma 2 goes to x gamma 1 gamma 2 y gamma 1 gamma 2, that is x compose gamma, y compose gamma. Let beta, which have components beta 1, beta 2 is capital F operated on del t, that is F operated on gamma. Moreover, for every t in AB, by chain rule we have beta dash t equals del x del u gamma 1 t gamma 1 dash t plus del x del v gamma 2 t gamma 2 dash t and del y del u gamma 1 t gamma 1 dash t plus del y del v gamma 2 t gamma 2 dash t. In particular, beta 2 dash t equal to del y del u gamma 1 t gamma 1 dash t plus del y del v gamma 2 t gamma 2 dash t, which is nothing but dy dt. So, integral over del t x del y del u du plus x del y del v dv, this equals with integral t equal to a to b x dy dt dt. So, it is integral over del s x dy. Here we use the result that inner product of mn and beta 1 dash beta 2 dash equals inner product of 0x and beta 1 dash b 2 dash, which equals x beta 2 dash. As the Jacobian is positive, the curves gamma and its image beta have the same orientations. If we started with assuming the Jacobian is negative, then we would find line integral over del t x del y del u du plus x del y du dv equals to negative of line integral over del s x dy. But from this also you would get the same result. Note, we know the above result can be extended to cases when first S is any bounded region in R2 with del S being a piecewise smooth Jordan curve. We proved the theorem assuming that S is a bounded rectangle. Next, in the proof we assume that the Jacobian determinant is non-zero everywhere. We can relax this by the condition the Jacobian determinant is non-zero except for a set of measures 0 on T, that is almost everywhere on the set T. Now, we shall discuss the geometric interpretation of the above result. Let us consider a continuous bijective map F from a region T in the UV plane to another S in the xy plane. Let F be described by the relation x equal to x uv and y equal to y uv. We fix a point, say u0 v0 from interior of T. If we keep u0 fixed and let v vary, we get a line segment in the UV plane parallel to u axis passing through the point u0 v0. We call such a curve a v curve. Similarly, we can find a u curve passing through the point u0 v0. Such curves are called coordinate curves. As the transform f is continuous, the image of these lines are curves in S. We have shown that in the adjacent figure. Now, let R denote the position vector xy equal to x uv y uv of any point in T. Then the components of the velocity vector along the u and v directions are respectively given by del r del u equal to del x del u del y del u and del r del v equal to del x del v del y del v. Now, we consider the rectangle whose diagonal points are u0 v0 and u0 plus delta u v0 plus delta u, where delta u and delta v are very small but non-zero. So, the area of this rectangle is delta u delta v. Now, the side with endpoints u0 and u0 plus delta u transforms into a curve of length norm del r del u u0 v0 times delta u approximately. This is because del r del u u0 v0 was the velocity vector and the corresponding speed is founded by considering its norm. For the side with endpoints v0 and v0 plus del v, the case is similar. For very small delta u and delta v, we can consider the transformed region to be a parallelogram. Its area is given by norm of vector product of the vectors del u del r del u at u0 v0 and del v del r del v at u0 v0. This equals to delta u delta v norm of del r del u u0 v0 cross product with del r del v u0 v0. Now, the term del r del u u0 v0 cross del r del v at u0 v0 equals with a notation like determinant ijk del x del u del y del u 0 del x del v del x del y del v 0 evaluated at u0 v0. Therefore, norm of the vectors del r del u u0 v0 cross del r del v u0 v0 equals with modulus of the Jacobian del xy del uv evaluated at the point u0 v0. This shows that whenever f transforms an elementary rectangle in the uv plane to a parallelogram in the xy plane, then the modulus of the Jacobian, that is mod del xy del uv at u0 v0, gives the magnification factor or scaling factor for the corresponding areas. If the value of the Jacobian is 1 everywhere, then the area remains unaltered. Next, let us consider any rectangle R containing the region T. Let P be a partition on R. We consider a subrectangle with a vertex u0 v0 and dimensions delta u delta v. For every small delta u delta v, the Jacobian del xy del uv is merely a constant. Thus, we can consider the Jacobian del xy del uv from R to the collection of reals as a step function, where on r minus t we consider its value identically 0. Now, the double integral of the Jacobian looks like summation mod del xy del u v delta u delta v. We let the ordered pair delta u delta v tends to 0 0. We find that this quantity approximates the area of S, that is double integral over S dx dy equals to limit of modulus del xy del uv delta u delta v as ordered pair delta u delta v approaches 0 0. However, in some particular case the Jacobian may be 0 at some points of t. Then such points are called singular points. At such points the vectors del r del u and del r del v are parallel to each other. So, the elementary rectangles transform into a line segment. If the collection of all the singular points is a set of measure 0, then it does not affect the integration. Now, we are in a position to state the required transformation formula and then we shall prove it. We consider a double integral over S fxy dx dy, where S is a bounded rectangle in R2. We also consider a bijective transformation between two regions S and T in R2 given by x equal to x uv, y equal to y uv, which are continuous and possesses continuous partial derivatives del x del u, del x del v, del y del u and del y del v on T. We further assume that the Jacobian determinant del xy del uv is never 0 on the set T. Then for any scalar field f which is integrable over the set S, we have double integral over S fxy dx dy equal to double integral over T f x uv y uv multiplied by the modulus of the Jacobian del xy del uv du dv. Let us denote J equal to modulus of the Jacobian del xy del uv. We have already proved that double integral over S dx dy equals to double integral over T j du dv. First, we shall prove the desired result for a step function. Since S is a bounded rectangle in R2, we can write S equal to as the Cartesian product of two bounded closed intervals a b and c d. Let small s be a step function defined over the set capital S. Then we can find partitions P1 of a b with intermediate points a equal to x0, x1 up to xm and P2 of c d with intermediate points c equal to y0, y1 up to yn, such that in every subrectangle of S formed due to the partition P equal to P1 cross P2, the map S reduces to a constant map. Let Sxy equal to Cij for every xy in the ij subrectangle, that is xi minus 1 xi Cartesian product yj minus 1 yj. We notice that summation over I equal to 1 to m, summation over j equal to 1 to n, double integral s dx dy equal to double integral t du j du dv. Now let Sij denote the ij subrectangle in S formed due to the partition P. Let Tij denote the preimage of Sij for this transformation. Clearly, Tij's are non-overlapping except for their boundaries. Now, delta xi delta yj equal to double integral over Sij dx dy equal to double integral over Tij j du dv. We multiply all the quantities by Cij and get the next step, which implies summation over I equal to 1 to m and j equal to 1 to n, Cij delta xi delta yj equal to similar sum over I and j, Cij double integral over Sij dx dy equals to similar double summation over I and j, Cij integral over Tij j du dv. Then using the additivity property of integrals from the above, we can write double integral over s sxy dx dy equal to double summation for I and j from 1 to m and 1 to n respectively, double integral over Sij s xuv y yuv j du dv equals with double integral over t s xuv y uv j du dv. That means we have proved the desired result is true for step functions. Next, let f be any bounded scalar field integrable over S. Since f is bounded, we can find scalar fields L and H such that for every xy in S, Lxy lesser equal to fxy lesser equal to hxy. Considering x and y as functions of u and v, the above relation can be written as L x uv y uv lesser equal to f x uv y uv lesser equal to h x uv y uv for all possible uv. We denote capital L uv equal to small l x uv y uv, capital F uv equal to small f x uv y uv, and similarly capital H uv equal to small h x uv y uv respectively. Then from the above relation we write capital L uv lesser equal to capital F uv lesser equal to capital H uv for every uv in T. We multiply the above three terms by j and then integrate over T. So, we find that double integral over T capital L uv j du dv lesser equal to double integral over T f uv j du dv lesser equal to double integral over T h uv j du dv. We assumed j to be positive such that this inequality is maintained. Hence, we can write double integral over S Lxy dx dy lesser equal to double integral over T capital F uv j du dv lesser equal to double integral over S hxy dx dy. Moreover, this is true for every pair of step functions L and H, where L assumes values lower than f and H assumes values higher than f, that is L lesser equal to f lesser equal to h over the set S. Since f is integral over S, double integral of S fxy dx dy is the only quantity satisfying the above inequality. Thus, we find double integral over S fxy dx dy equal to double integral over T f uv j du dv. This completes the proof. Another remark, like the previous case, the above result can be extended to cases when first S is any bounded region in R2 with del S being a piecewise smooth Jordan curve. Second, the Jacobian determinant del xy del uv is non-zero except for a set of measures 0 on T, that is almost everywhere on T. Now, we discuss some elementary transformations. First one, from rectangular Cartesian coordinate system to polar coordinate system or its inverse. Here we take u equal to r and v equal to theta. Here the laws of transformations are x equal to x r theta equal to r cos theta, y equal to y r theta, that is r sin theta. To make the mapping bijective, we take r greater than 0 and theta belongs to a semi-open interval of length 2 pi or less. We notice that the Jacobian of this transformation is given by j equal to r greater than 0. For this transformation, the r curves are line segments which when extended passes through the origin, and theta curves are circles or circular arcs whose center is at origin. A rectangular in the xy plane corresponds to a region bounded by two line segments of same length and two circular arcs subtending the same angle at the origin or an annular region. We prefer polar coordinates when the region of integration has boundaries along which r or theta is a constant. Next, another transformation which we frequently use is scaling maps, which is given by x equal to alpha u, y equal to beta v, where alpha and beta are non-zero constant. We know that this is a special case of another linear transformations which we frequently use, which is given by x equal to alpha u plus lambda v and y equal to nu u plus beta v. In this case, we can observe that the Jacobian should be non-zero. Since a linear transformations preserves linearity and parallelism, such a map transforms a rectangle into a parallelogram. We cite an example. Let us consider a mapping defined by the equations x equal to u square minus v square and y equal to 2 uv. We calculate the Jacobian determinant and find that this equals with 4 u square v square. Now, we suppose a rectangle T which have the vertices a 0 0, b 1 0, c 1 2 and g 0 2 in the uv plane. Under the given transformations, these vertices are mapped to the points a dash 0 0, b dash 1 0, c dash minus 3 4 and d dash minus 4 0 in the xy plane respectively. And these points will be the vertices of the region S in the xy plane. Now, to find the image S of T in the xy plane, we will find the images of the boundaries of the rectangle T in the xy plane under the given transformation. We find that under the given transformation, the line segment AB, which is given by v is equal to 0 and u belongs to closed interval 0 1 in the uv plane is mapped into the line segment a dash b dash joining the points a dash 0 0 and b dash 1 0 in the xy plane. Next, the line segment BC, which is given by u equal to 1 and v belongs to closed interval 0 2 in the uv plane is mapped into the arc b dash c dash of the parabola y square equal to minus 4 times x minus 1 joining the points b dash 1 0 and c dash minus 3 4 in the xy plane. Thirdly, the line segment CD, that is v equal to 0 and u belongs to 0 1 in the uv plane is mapped into the arc c dash d dash of the parabola y square equal to 16 times x plus 4 joining the points c dash minus 3 4 and d dash minus 4 0 in the xy plane. And finally, the line segment DA, which is given by u equal to 0 and v belongs to 0 2 in the uv plane is mapped into the line segment d dash e dash joining the points d dash minus 4 0 and a dash 0 0 in the xy plane. We have shown that by this figure, thus the region S in the xy plane will look as this. Finally, we evaluate the double integral over gamma xy dx dy by making the change of variables x equal to u square minus v square, y equal to tuv, where gamma is the region in the xy plane bounded by the unit circle. Under the inverse transformation, the image of gamma in the uv plane is given by d equal to collection of uv, where u square plus v square is also less or equal to 1. Therefore, we have the required double integral equals double integral over d u square minus v square 2 uv, the Jacobian modulus du dv, and we find that after some calculation it is 0. So, in this module we studied the change of variables in double integrals. So, given any double integral, we can now substitute the variables to make our life easier. We conclude here.